Bayesian model, machine learning find probability of network information. View this. It is easy to lie without statistics. It is hard to tell the truth without it. Identical. In Bayesian network, the state xi is conditionally independent of its ancestor, given its parents. Therefore, we will get this equation. The only rule of Bayesian model is probability of a node is conditionally probability of its own, given the probability of its parent. For the first example, as you can see, the network is connected in series. A is joined to B, B is point to C, and C is point to D. So the joint probability of A, B, C, D is going to be PA multiplied with PB given A, multiplied with PC given B, multiplied with PD given C. For the second example, here we have the node A given its two ancestors, which is node C and node B. For the node D, it had two parents, node C and node B. So for the joint probability of PABCD, gonna be PA multiplied with PB given A and PC given A. For the last one, it's gonna be PD given B and C. This one gonna be like a mix with 5 nodes, 5 variables. As you can see, B and A has only one its own ancestor, which is C for the B and D for the A. D for the A. And also, the node E is only one ancestor of the D. But for the node D, it had two parent, which is C and A. So this is going to be the mixed node. Then the property of A, B, C, D, E is equal to PA, then PB, then PC given B, multiplied with PD given A and C, multiplied with PE and D. Okay, let's summarize of it. So now we will see that we have three kinds of connection. For the first one is head-to-head. For example, this network, we have ABC node. We will try to find what is the property of PA joined to the B. That we call it head-to-head. Next one is head-to-tail. And the next one is tail-to-tail. For the first one, head-to-head, the joint property of ABC is not complex at all. It's equal to PA given C, B given C, and property of C, like what we talking about it before. But for the property of only head-to-head, which is PA to B, it's gonna be the summation of S. Sorry for wrong variable here. It should be the summation of C, because we find the property of A joined to B. So the variable C or node C is not given. So we have to use the summation sign to get this. So property of A and B gonna be summation of C for the property A given C multiplied with PB given C and property of C. For the conditional property, P of A and B given C is going to be P of A given C and P of B given C. Or can call it is equal to property of head given its tail. For the head to tail, in here we have the B on the head and the A naught on the tail. Let's start at property of A, B, C, joint or the joint property. It goes straightforward. It's going to be property of A multiplied property of C given A multiplied with property of B given C. For the property of A and B or head to tail, it is a summation of PA, PC given A, and PB given C. Remember, we have to use the summation on the node that we doesn't given its parameter. And lastly, for the conditional property PAB given C is going to be straightforward. PA given C multiplied with PB given C. For the tail to tail, in here we have A and B with its tail of the head that is C. For the joint property of ABC, here is straightforward. Again, it is PA, PB multiplied by PC given B and A. For the property of tail to tail or PA and B is equal to PA and PB because in here you can see that PA and B is independent when we not given the C value. But after that, when we give the C value, it's going to be like the last equation, PA and B given C, or conditional property. It's going to be PA, PB multiplied with PC given BA and divided by the property of C. Because for now we have the conditional that C has to be some value. So it's not gonna be like the second line equation anymore. So that is we just communicate with the conditional probability distribution. So let's say it is the example for today. What should I call it? Today clip video, right? This is my second video for the AI course. And yeah, this is the example. We will call this model as a job model. It's explain how we can get a job from before we get into the university. As you can see, we have the mix node, like we have the genetic node and practice node on the first level, and the second level we have university level, and the last level we have the jobs. Okay, we will go to the genetic. The genetic node is represent for whatever you have a good genetic or bad genetic, like you are a smarter guy when you born, or you just normal people since you born. And the practice is mean you have a good practice by your own or bad practice, like you try to coding by yourself without go to school, without a knowledge from university. And for the next level, university will have three output, like we have good, normal, and bad university. And for the input, the input of university is represented by its index. We have good gene, good practice, and the next one is good gene, bad practice. Next one is bad gene, good practice, and the last one is bad gene, bad practice. And its index and its column will be represented by its percentage. How to call it? It will be assigned by its probability. As you can see, its law of university should be summed to 1. For example, the first one, good gene, good practice, is that bad for 0.5, normal for 0.3, and good for 0.2. So that the sum will be 1. also for the second, third, and fourth line. And the last level of job, it will have two output here. The output will be, yeah, you know job, it means you don't get any job. And the second output is you get a job. And the input will be only 3 input, because the university have its own 3 output, right? So the job has to be its own 3 inputs from the university. So we will have bad university, normal university, and good university. And again, is the summation of its law will be equal to 1 again. For example, the bad university input will have 0.95 and 0.05. That is 1. Python Python. Hey, again, we use the Python to find is how to call that? Let me go back. We will use Python to find the conditional probability distribution. Okay, and first, as always, we import libraries. Today we will use PGYPY class to solving the probability distribution. But anyway, if you want to use the PGMPY, you have to install it by calling something like pip space install space PGMPY firstly. Then we set up the model structure. So in here we will call the model, which is job underscore model, using the Bayesian model. And then we name all the network, how its network is connected together, right? For the first line, we have genetic connected to university, and the second line we have praxis connected to university, and the last one we have university connected to the job, as we seen before here, right? For next one, we will set up the relationship of conditional probability distribution, and here these are the setup of relationship. Each variable will be called by suffix CDP or conditional probability distribution, or I just write a wrong word here, sorry for that. Additionally, we have genetic CPD, praxis CDP, or I made many wrong here, sorry about that. University CDP and job CDP. And yeah, each variable will be defined by tubular CPD function. As you see, we use the tubular CPD function, CPD function, tubular CPD function, and tubular CPD function. And let's see how its parameter should be adjusted. The first parameter is variable. The variable is called for node calling. Variable underscore guard, it should be the dot here, sorry for that again. Variable underscore guard is for showing how many categories it has. For example, we have the practice underscore CDP here. We assign the variable to be the practice from the previous page before. And the variable underscore guard is equal to 2. What does it mean? It means that the practice will have 2 categories of output. For the first one, 0.7 is represent yes, we have a good practice. And the second one on the value, right? 0.3, we have no, it means we have a bad practice. Yeah. And also for the university CDP on the value, the first line of value is represent the probability of we get the first category of university, which is bad university. So why we have 4 number here? So the 4 number here, because we have 4 input. We have 2 input from the genetic and 2 input from the practice. So to get the output of bad university, we will have 4. We have 4 chance to get bad university, right? The first one, as we talked about it before, alright. Remember, we have we have 4 chance to get bad university. And why? Let's come back to here. As you can see, the bad university, we it can generate the bad university by 4 conditions. The first one is good gene, good practice, then good gene, bad practice, and so on and so on. And so on for the normal university, and so on 4 chance for the good university. So the first line is for bad university, second line is for normal university, and the third line is for the good university. And here the next variable is evidence. Evidence is showing its own parent. For example, come back to our university CDP. The evidence is genetic and practice. What does it mean? It means that it's telling the network how it's connected together. In here, university is the ancestor of the genetic and practice. So we just define that. And the last one, evidence underscore guard, is the value of its parent category. What does it mean? It means each assign how many output from its evidence is. In here we have genetic, which is 2 output. So we define it 2. And practice had its own 2 output, so we define it 2. And I think if you define it wrong number, it's going to be error. Some errors text show here. And as you can see for the last one, the evidence guard of the job, we have 3 because the university have 3 output goes set into the job node, right? Because we have bad, normal, and good university. So the evidence guard of the job will be 3. And please remember that evidence guards have to assign in the list function. For example, for the university, we have 2 for genetic, 2 for the practice within the list function, the square bracket here. Okay, then we will add this CPD, conditional probability distribution, information into the job model before call the get underscore CPDS function to examine the overall structure. So what does it mean let's release the hashtag first. Add relationship into model. Oh yeah, so we just define the job underscore model. So we will call the function add underscore CPDS, and we will assign all the value that we just defined in the previous page here to get the program to know which parameter, which variable we will use for this network, and they will examine the structure of graph. So we will call the function get underscore CPDS function, and the program will be generate some output to let you know how its node is connected together. But I don't think that I pin it here, so it's a lot. This page is full for that, so let's try it yourself. And then we will find active tail node. To examine how its node is active, we can call active tail node function to see how a node is connected from head to tail. As you can see from output figure on the right, local underscore independency of university is equal to empty, as it should be. But for the first one, the active underscore tail underscore node of the genetic, as you can see from here, the genetic is independent to the practice. Also, the practice is independent to the genetic. It should be the output from these 3 lines, right? But for the local independency of university, as you can see, it's like a blanket of output. Yeah, it's empty because university is known of independency. And the last one is the function get underscore independency. It it will tell you all the impedancy in the network. It will be used when we want to see all impedancy, but in the real network you will not do that because the network will be right. It's very complex to see, so it's more likely that you will be better to see only one node local independency. Okay, for the next one, to get probability distribution, we will call the Curie method. For the first example, we get probability distribution. But before that, before we get the probability distribution, we have to define the inference. Like, so we just write here the job underscore inference, like is equal to, you have to call the function variable elimination of the Bayesian model that we assigned before. So we call variable elimination of the job model. And here we will use the Curie function to find the property of job. So basically just define new variable. Property of job is equal to job underscore infer that we assigned before. Dot Curie round bracket variables equal to in the square bracket with the string jobs. So we will have here the property of we get is job. For the job 0 and job 1, job 0, you remember that job 0 is mean no job, don't get a job, and job 1 is right, it is yes job, it means yeah you get a job. Oh, it is really low here, you only 11.02% get a job. Oh man, do I get a job? Okay, so the next one, get conditional probability distribution. In here the difference from the first example and the second example is we join the probability together. For the first one we have probability of jobs, but the second one we have joint probability of jobs and genes. Let's see the output here. So in here we have 4 output, like because we have 2 input. Yeah, the gene 0, job 0. Yeah, let me say that in the real human world, right? We have good gene, good job. No, sorry for that. Good gene and get a job. Good gene, no job. Bad gene, get a job. And bad gene and don't get a job. And the output here is the probability output that we get. So let's see if we have a bad gene but we get a job. So 1 0. Oh my god, how can it so high? By the way, the input is not a real input. I just let know the number here. Yeah, so let's say also for the joint and conditional probability can use the Curie function for the parameter variable is foresee how CPDS conditional probability distribution. It will be exam. Even it for adding the conditional probability. Oh yeah, we talked about it before. And the last one is yeah, the different. Let's see this example, the third example. As you can see, the evidence here use the, how to call that, the bracket size to assign the evidence to be only one given number. So let's go through the previous page. The previous page the previous page here, University CDP, we use the evidence is called through genetic and practice, right? Remember university, genetic, practice. Go back. Oh yeah, and here we assign the evidence here for the genetic with a semicolon and 1 to given the gene had to be only the bad gene. So we will find the probability of job when we given the evidence of gene to be bad gene. yeah, it just translate from the Python language to the human language, like, and we will print it, and we will get this. The output of is job probability given the gene is equal to bad gene. For the next one, let's read it first. Also, we are able to go upstream logically to see how its input conditional distribution properties, not property, sorry for that, probabilities will be when we fix the output. And yeah, because we just go upstream logically, so it means that we try to give the evidence that is the downwards node. It means the last node. Like for example, here we given the evidence by the university, and we try to find with the variable is gene. So you remember the gene is upper node and university is lower node. So we can write it mathematically by probability of gene given university is equal to something. In here we assign the number 2 with is good university there, and then we will get the output like here, the probability of each gene. For example, here we see the conditional distribution property, not property, what is it? Conditional distribution probability of gene when we observe that university is a good university, right? So, and yeah, in this example, I just use the comma to connect more evident, more given condition here. And remember that this parameter has to be in the brackets. For the variable and evidence that are able to these are able to be more than one variable, we can use the bracket, oh yeah, I call it correctly, brackets, and colon to adjust the evidence parameter. Let's go next. Oh yeah, we come to the last pages. Thank you everyone to see how I present this video. Thanks for that. Thanks for listening me. Okay, lastly, we can all it should be we all can. I write the wrong word again, sorry for that. And lastly, the infer.map qly, we use the function to see which category of its node which is most likely to occur. And yeah, that is the most probability state for the variable. It's basically just put the map underscore qly and assign some variable in here to get what most likely should be for the variable that given. For example, we given the variable to the university to get to know what which type of university will be generated mostly. So here we will get that, let's see, we will get most likely to occur for the genetic is bad, genetic practice is good, practice, oh yeah, so bad luck born people like not good genetic people were born, and then they practiced a lot, did a good practice, and then they got a bad university, so they don't get any job. Oh, so sad, so bad, so sad and bad. Oh yeah, so then we have it all. Okay, again, thanks for anyone who try to understand me for the second video I made it. If you have any comment or anything I have to fix or anything you want me to know, that please let me know on the comment, right? Anyway, thank you. And this.